Okay, welcome to the lecture of image analysis in CASA. Hello, my name is Feng Long, a current SMA postdoc fellow. So in the previous lecture, we have learned how to make an image using data taken by the interferometer. In what follows, this lecture is going to introduce some basic analysis that we usually perform with those images. This will hopefully provide a more practical view of what kind of science results that we should be expecting. So depending on the observational setup or the specific science goals, there are two kinds of images that we usually produce. A continual emission map is a simple 2D position diagram. Well, if you are interested in spectral line observations, you will obtain an image cube with a third axis describing the velocity information of the target. In this lecture, we will go through how to extract basic information from the image, like peak intensity, total flux, noise level, as well as the emission size. For image cubes, we will also cover the extraction of spectral line profile and the construction of wind maps. Those kinematic information are provided by the additional velocity dimension. All of those analyses can be performed with CASA. So CASA is the software that we use to calibrate and image our data, which also contains a long list of tasks specific for image analysis. This makes our life much easier. So this long list can be broadly divided into a few categories. First of all, we can view and access what is included in the image. So tasks like ImHead and ImView, they can do that. I will show more details later. Then we can modify the image content. For example, by making a new image that is only a part of the original image. We can do simple maths with it. We can also reformat the image by changing the image coordinates, blur the image by restoring the emission with a larger beam. This will help us to better view the large-scale structure. There are also many fitting tools that can fit 2D emission profile or to fit 1D line profile. Lastly, there are two very useful tasks to convert the image format between CASA images and FITS images. If you would like to further process your data outside CASA, we will usually write the CASA image into a FITS file that can be read by other packages. Well, many of those image analysis tasks in CASA can also operate with FITS images, but it is always safer to convert them into CASA image first. This is because they may have different handling on the ordering of image axes, and that can produce some internal errors in the operation. But if you only want to view the FITS file with CASA, there's no need for conversion. That can be easily done. So in the next steps, I'm going to introduce some commonly used tasks in detail and with some tips in using them. Let's start with ImHead. So ImHead is a task for us to access the image header information. It is very important in the first place to get an idea of the data structure and the basic information of the observation. If you put this command in your CASA shell, here is the output, which shows a list of the header information. I have broadly named the content into a few categories. As you can see, this data set is for HO tau, which is taken in 2017 with ARMA. And the data is at a rest frequency of 280 gigahertz and restored in a clean beam of about 0.1 arcsecond. But this image has 4 axes. So the third axis is for frequency, which has a shape of 1. This means that this is a continuous image. A spectral line image cube will often have an array of frequency. So this is only to list the header information. We can also modify that information by setting the mode parameter into put, but only do this when you are 100% sure what you are really doing. Otherwise, you might make some problem for the further analysis with CASA. So with this information in mind, we would like to view the image directly. So the CASA viewer is designed for it. This is the interface of the CASA viewer, which can be launched by calling the in-view task in the CASA shell. So the image is now showing on the left. There are also a few panels on the right-hand side displaying different functions of the image. So if an image cube or multiple images are loaded into the viewer, the upper panels will guide us through different image planes. We move your cursor around the image. This middle panel for the cursor panel will keep track of the information in that pixel, where your cursor is located. Then we can also define a region in the image. In this example, the region is marked by the magenta circle. In that case, once the region is defined, the region panel will display many useful statistical information of the data inside that mask. We can draw different kinds of masks in the viewer. There are a few options for you to choose for different selection tools. We can draw a box, a circle, or any shape that you can draw on top of it. This interface also contains many interactive tools as a quick access to the image analysis procedures that we will discuss later. So the first question, how can we obtain the data values from the image? As I just explained, the cursor panel in the viewer will display the pixel information, which includes the intensity of that pixel in the image as defined by your cursor. So we can read out from this snapshot. So in this case, at this pixel, the intensity is about minus 9.7 10 to minus 5 Jansky per beam. This information can also be obtained by calling the in-view task within the CASA shell. So in this case, we can specify the pixel location with the box parameter. A Python dictionary will be returned, and we can access any information as needed. So this is only for extracting data in one pixel. What if I'm interested in the data in a larger area? How can I do it? We then need to set the region parameter in in-view. So before that, I would like to first introduce these widely used data selection parameters in CASA tasks. As just showing that if we use 2 coordinate values defined in the box parameter, this describes 1 pixel in the image. We can also use 4 values. This will define a rectangular region. So the first 2 value is for the pixel of the bottom left corner, and the last 2 value is for the pixel in the top right corner. The 2 pixels will help us to define a box. Meanwhile, we can use in the region parameter, which have more flexibility. We can use it to define a circle or many other shapes of interest. In this example, I'm using a circle. A circle will require you to define the coordinate for the center and also the radius. So this is for command use. Within the viewer interface, we can also draw a region with any shape and save that shape as a region file. And that region file can also be called by the region parameter and used in those commands. So by specifying the region or box parameters, data value within any region you're interested can now be extracted from the image with this in-view task. So within any specified region, we can then perform simple image statistics. In this example, statistic information within this magenta region is now summarized in the region panel of the viewer interface. There are a few parameters that we should usually pay attention to. So first, the maximum value. It describes the peak intensity of the source. The flux density value, it describes the total flux of the source emission. In case of an unresolved point source, the peak emission is usually equal to the flux density. Such statistical information can also be accessed with the task imstat. We can either print out our results in a terminal or save them in a text file for further usage if we can specify the path and name using the log file in the imstat task. So this is the way that we extract information for the signal, for the emission. How can we evaluate the noise level in the image? The noise level is usually reflected by the RMS value in the image background. So that means we have to specify a region outside from the emission source. However, the selection of this region should also not be too close to the primary beam edge because the sensitivity drops off very quickly around those edges. In practice, we would like to include a large area for this noise calculation that can help us to average out any artifacts in the background. So in this example, I used ananas, which encompasses all azimuthal directions in the background. This RMS noise level is often mentioned alongside with the peak brightness because this will help us to describe the image dynamical range and also the significance of the detection. For example, we usually see the source is detected at a few sigma. That is described by the peak intensity and the RMS value. So in math, this is a task that we can use to perform mathematical operations on images. This task will generally modify the data values in the image. We can perform math on a single image. So the example here shows how to get the square value of each pixel in the image. We can also operate it between images. So this example shows how we can subtract value in the first image from the second one. We can also use this task to calculate the emission spectrum index. This is a quantity that is widely used to describe the nature of the emission source. So when operating on multiple images, we have to keep in mind that a meaningful result will require the emission restored in a clean beam with the same shape. If T-clean has resulted in different beam shapes, we need to first convolve the two images into the same shape. And this can be done with the im-smooth task. We can specify the target beam shape and setting the target resolution as true. This is particularly useful when we try to compare the source properties in images with different original beams. Usually data taken at different time epoch or with different telescopes can have a different beam shape, and this can be then compared by first smoothing them to the same beam, same restoring beam. Video profile. It is a very useful way to visualize the emission structure. So CASA viewer provides a quick but kind of dirty way to do it. In this example, I'm interested to see how the emission changes along the source major axis. So these line segments can be first defined using this line drawing tool in the toolbar. The extracted profile will then appear in a new window. So from which we can tell that the emission profile is mostly Gaussian, and the emission extends to about 0.2 to 0.3 arcsecond on each side from the peak center. You can also save this profile into a text file and plot it later on with your favorite software. This can be as a quick way to roughly estimate the emission size. And CASA also offers other fitting tools that can produce more quantitative results of the source emission information. So in viewer, this button encodes the tool for 2D Gaussian fitting in the image plane. By clicking this button, the interactive fitting tool will appear. We can then set up the fitting by selecting specific regions of interest or providing some initial guess for the fitting. This fitting is quite quick. It usually takes a few minutes to finish. Of course, this convergence requires that the emission can be well described by a 2D Gaussian model. So this tool has its own limitations. But in this Gaussian framework, we are usually interested in the emission size. You will notice that in the returned results, there are two sets of image sizes provided. One is the direct fitting results, and the other one is the deconvolved size from the beam. So the latter one, the deconvolved size, would resemble more of the intrinsic source size. This whole procedure can also be scripted within the CASA shell using the task imfit. Here I provide a simple example on how to perform it and how to extract the fitting results. You may notice the keyword of component 0, which means the first or the only component in this fitting scheme. What if I have multiple sources in the image and I would like to fitting them together? ImTask also includes such functionalities. However, this would require an additional input parameter as a prior estimate for the source properties that estimates should be specified in the imfit task. Alternatively, such fitting can be performed in the UV plane using the UV model fit task. This task works directly with the visibilities and may largely diminish possible artifacts associated with the clean process. So in the previous discussion, we have focused on 2D imaging. For spectrum line observations, the added velocity axis provides more rich information on the emitting source properties. The inclusion of a third dimension offers many interesting ways to view the image cube through projections, through different ways of projecting the data. And this is the key concept of most image analysis procedures of 3D data cubes. Well, before we dive into the details of those analyses, I would like to make two notes. First, we have to make sure that the continuing emission has been subtracted out in the line channels. Otherwise, the interpretation of the line emission can be quite misleading. We usually recommend to finish that step before making the image by using the UV count subtask that operates directly in the visibility domain. If this is somehow forgotten, you are now giving a second chance to correct it. In the image plan, we can use the im count subtask to do the same, basically have the same function. Secondly, if somehow your initial image cube is really, very large, which might take a long time to load and to operate, we can resize the image using the im sub image task. For example, we can choose some limited velocity channels or some emission region of interest. This can largely speed up the whole process. So let's start with moment maps first. Moment maps are often reported in papers as valuable science outputs. Moment maps are 2D images, which are produced by manipulating individual image channels across the velocity domain. So they fold information of the intensity with velocity and provide different viewing angles of the data cube. If you're looking at the documents, there are a long list of different kinds of moment maps. But the first three kinds are most popular and widely used. So I will focus on the first three kind maps. Moment zero map is also called an integrated intensity map. It is the sum of emission along the velocity axis in each pixel of the image. So in this way, the integrated line intensity can be obtained through the image by summing up all the emission there. The second and the third map are related to the velocity field. The first moment map is often referred to as the velocity map, and the second map is called as the velocity dispersion map. So we can simply understand this as taking a line profile in each pixel. The momentum one value describes the central velocity in that profile, while moment two value describes the line weights. When computing those higher order maps, it is important to set a threshold to only include pixels with significant emission. So in this example, I'm setting a clipping to 3 sigma of the emission in individual channels. In cases of complicated velocity field, where both emission and absorption present, the interpretation of the moment maps can be quite tricky. So in such cases, viewing the channel maps would be more demanding. So channel maps are 2D slices across the velocity axis, which shows how the spatial distribution of the line features changes with velocity. This example shows a capillary rotating disk that the typical butterfly pattern is clearly seen. We can further reduce the data dimensionality to obtain a 1D line profile. So this is an example line profile obtained with the CASA viewer. In the viewer, once we have first defined a region, this line profile window will appear when we're clicking on this spectrum line tool. So line profiles are very useful in determining how many velocity components present in the system. And it is also convenient to visualize the relative amplitudes of different components. We can also use Python scripts to directly extract the spectrum. So InView again will be used for this task to extract the data value in the image. However, in this case, we also need to specify the velocity or frequency axis. This part will then make use of the image header information. So here, I only provide a simple example for your reference. Okay, the last tool, PV diagrams, which are also commonly used in papers. It shows how the velocity emission changes as a function of positions in the map. So specific kinematic motions of source will have characteristic velocity pattern with radius, like inflow, outflow, or rotation. You can have some analytical function to describe the velocity with radius. So PI diagrams will be helpful in diagnosing such system kinematics. In viewer, we can use this button tool by first specifying the interested positions in the map and then generate the PV diagram. Similarly, we can also use the MPV task for this construction. Both have the same, should give you the same results. So in this very brief introduction, many tasks are not covered and many parameters that you can play around in each task are also not discussed here. You could take a look at the CASA notebook for the details of each task. CATA is different outside, it's outside of the CASA environment. It is a new tool that is in active developing recently, specific for image visualization, which covers most of the tools we just described. So you may want to pay attention to this tool in the future use. More than often, the results and the figures we present in papers are not directly produced by CASA. So each of us may have our own routines or Python scripts for the image analysis, but there are a few commonly used ones. The Spectra Cube is a popular CASA package that many people use. Better Moments can produce better looking moment maps. This is a package developed by Rich Teague, one of our SMA fellows. So all those packages and tools should be useful in your future research. That being said, CASA Viewer is still very valuable to provide an initial quick view of the data information. So I would like to spend a few minutes to guide you through the viewer. Okay, so in this CASA shell, we can launch the CASA Viewer by typing in view task. When you've done that, the display panel will come out. We can then open a file. So first, let's do a continuous image. Once you select a file, some basic information will be displayed here on the right-hand side. For example, the shape of the data and also the restoring beam. When we load it into the CASA Viewer, we can zoom in and zoom out to see the details of the emission. Those toolbar has some very useful functions or tools for us to use. For example, when we select this button, we can drag the emission to any specific points of the view window. For example, we would like to put them at the center of our view window. Those two buttons are used to adjust the color scale of the image. For example, this can, if you drag your mouse up and down, you can see how the color scale change and the emission can be highlighted from background noise. And this button is to change the brightness of the color. So this dragging the mouse, it will become brighter and darker. In the next four tools, they are used to select regions. For example, this is for a box region. Once you have defined any region, the region panel will show the corresponding properties. Especially the statistic sub-channels will tell you the information inside, a value inside this box. When you move this box around, and the data points in the statistic results will change accordingly. You can also try to draw any region of your interest. Let's see, we can draw a shape like this, and then double click in the last point to define a closed region. And we can also drag the points to make corrections to the region we just made. Another interesting part is that we can save this region file. And once you save it as a CASA region file, this file can be then used in other tasks when defining the region parameter. This tool is for you to add a line segment in the map. So if we make a line along the disk minor axis, now a line profile will come out at this region panel, and we can enlarge it to have more detailed look and save the file for further analysis. This is called a ruler tool. It can help us to directly measure the size of the emission. For example, we can draw the ruler, and then the scale of different direction of the triangle can be measured in arcsecond. And so these are basic functions we usually use for the continuum emission. Now, if we close it and open an CO image cube, this channel panel will now be active. We can click this button to go through different channels and see how the emission changes. And alternatively, we can view multiple channels at the same time. This requires us to modify the views setup. We can have two channels, 2 panels, 4 panels by setting the number of panels in different axes. We can also adjust the margin values to have a better view of the emission. So if now we go through the different channels, we can compare the emission directly in one view, how the emission changes across different velocity channels. Now, if we can define, if we can define a region by clicking this button, a line profile can be viewed, and some analysis can be also operated in this bottom part of the spectral profile viewer window. So those are the basic tools that we would like to use with CASA Viewer. Hope you have learned something here, and thanks for watching. I'm happy to have more discussions during the school.